Welcome to Unit 5, Simple Harmonic Motion. Let's get started. We're going to start off looking at spring systems, and then we're going to look at pendulums. Those are the two systems we're going to be looking at. So let's start with simple harmonic motion in spring systems. So what do we mean by simple harmonic motion, or SHM? Basically, simple harmonic motion involves any kind of system in which an object is going to continually alternate between having kinetic energy and having potential energy. So systems that exhibit simple harmonic motion will have what we call an equilibrium position. And in this equilibrium position, all the forces acting on it are equal to zero. So at this equilibrium position, it has no acceleration. All right, now we're going to find out it has a lot of motion at that point, but no acceleration. So uh, because the sum of the forces here at equilibrium equals zero, that if I put an object here and release it at this point, there's not going to be any motion in the system. It's just going to be at rest. It has no mechanical energy if it starts off at its equilibrium position. However, if I take that object and I displace it from its equilibrium position, then I'm going to be doing work. I'm going to cause it to gain mechanical energy, and at that point, when I release it, that mechanical energy that I put into the system is going to stay there, provided that the forces acting on it are conservative forces acting within the system. In this case, I have a frictionless system with an ideal spring. That means the spring has no mass, no friction associated with it, doesn't dissipate any energy. If that was the case, this object would just go back and forth forever, exhibiting what we call simple harmonic motion. And there's certain aspects of simple harmonic motion we want to come to understand in this unit. They're really not that difficult, fortunately. Okay, the main thing about simple harmonic motion is it exists because there's what we call a restoring force that acts on the system that pushes it back towards this equilibrium position. I'm going to say it again. In order to have simple harmonic motion, you have to have, among other things, a restoring force that is going to push the system back to equilibrium if it's pushed out of equilibrium. All right. But the other thing that's really important is you can get it to oscillate, but for it to exhibit what we call simple harmonic motion, which has these equations that we can apply, then the amount of restoring force has to be directly proportional to the amount of displacement. In other words, displace it twice as far, and you will have twice as much restoring force. If that is the case, it will exhibit what we call simple harmonic motion. Now, a classic case of that is a spring, right? Because if you remember the spring equation, the force exhibited by a spring is equal to the negative because it pushes if it's pulled and pulls if it's pushes, but of the spring constant times the displacement. So if I double the displacement, I will double the force exerted by the spring. For that reason, springs are a classic example of a system that exhibits simple harmonic motion. So amplitude is another measurement we'll have in these systems. So amplitude is really just a way of referring to the maximum displacement the system has from its equilibrium position. So let's just say this is the equilibrium position. I push it distance x, compressing the spring. I'm going to get a certain amount of force here, restoring force of F. If I then displace it instead 2x, if it's going to exhibit simple harmonic motion, that means I'm going to end up getting 2F the force. All right. And that's what we have with springs, right? Because if you double the displacement of a spring, you double the spring force. So therefore, it's going to push twice as hard. And in this case, it will exhibit simple harmonic motion. So the point is, amplitude is simply how far the system is displaced from equilibrium. Here, the amplitude is x. Here, the amplitude is 2x. Now, the period of an oscillation is simply the time it takes it to complete one oscillation. All right. So if I look at the system here, I'm going to wait till it reaches a maximum displacement right here. And then this time here, it takes to get from here and back to here, that time is going to be the period of it. So let's just count Mississippi's as what I grew up doing. Okay, 1 Mississippi, 2 Mississippi, 3 Mississippis, 4 Mississippi. It's about 4 seconds is the period of that oscillator. So it's just the time it takes to complete one full oscillation. That means from maximum displacement on one side, back across equilibrium, and back to your starting point. That would be one complete oscillation. Now, period is the time needed to complete an oscillation. That's usually how we're going to refer to the time interval associated with an oscillating system. However, how do I say this? Often in the past, College Board would teach this in concert with a concept called mechanical waves. And with mechanical waves, they often oscillate much faster. It's like a tuning fork. It oscillates much faster than one cycle a second. So in that case, you switch over and you talk about the frequency of oscillation. Now, I noticed that some of the questions in College Board's release items still refer to frequency. Now, here's the thing. Frequency isn't that hard to get your head around. It's just the reciprocal of period. So instead of saying how many seconds per oscillation, let's just say it took 5 seconds to complete it. Now let's make it easy. 4 seconds to complete an oscillation. If I flip it around, then the frequency just mean, well, one oscillation took 4 seconds, so it'd be the frequency would be 0.25. So frequency is just the reciprocal of period, and period is just the reciprocal of frequency. Now, period we measure in seconds, frequency we measure in hertz. So a hertz means 1 cycle per second. If somebody's making a 60 hertz sound, that means it makes 60 oscillations per second. The truth is, we're unlikely to see frequency very often, but sometimes we do. And if I'm going to use the simple harmonic motion equation we're about to learn, I have to remember that frequency is the reciprocal of period. So I have to take the reciprocal of the frequency in order to get period. Sorry about that. I know it's a pain. So now here's the big equation of today. The big equation of today is this. This is the equation for the period of a spring oscillator. And you do need to memorize this one for our next test. But you only have 2 equations to memorize for our next test, so don't come belly aching to me. So the period of a spring is equal to 2 pi, which is just a constant, times the square root of this fraction, mass over spring constant. Now let's think about this for a second. If mass increases, the acceleration is going to decrease, so it's going to take more time to complete an oscillation. If K, spring constant, is increased, then the storing force is greater. There's more force, so it's going to accelerate faster, and therefore take less time to complete an oscillation. So this does make sense. Now, let's just apply this here. Okay, so I have a spring oscillator here, has a period of T1. Okay, that's what we call the initial. Okay, what would the period T2 be if I double the mass? So now I take this, I'm going to double the mass. So I'm just going to look at my system here and say, well, how is it that the period of a spring is proportional to its mass? Well, T is proportional to the square root of the mass. So if I was to double the mass, then I would have to get root 2 times the period. It would take 1.4 times longer, root 2 times longer. Because remember, the period is how long it takes to complete. Well, let's show this. What if I had the same thing, but now instead of doubling the mass, I'm going to double the spring constant? Well, now I'm going to go the same thing. Now remember, I am increasing the restoring force, so it should take less time here, right? It's going to accelerate faster. So the period is proportional to 1 over the square root of k. So if I double this, then I would have 1 over root 2. So that means the new time here would be equal to the original time times 1 over root 2. So that's going to be a small value. And so that means it takes less time, which makes sense. What if I changed the amount of displacement? So the amplitude of oscillation was doubled. Well, now let's think about this. That's not part of my equation. Turns out it does not matter how far this thing oscillates from equilibrium, because the more I displace it, the greater the force, the greater the acceleration. It turns out it's going to complete that oscillation in the same amount of time. So looking at the equation, the amplitude of the displacement is not a factor in this. So it doesn't change it at all. Now let's talk about how we're going to use graphs to analyze simple harmonic motion. So if I was to take, say, a motion sensor and measure how far an oscillator goes back and forth on either side of equilibrium, or I could measure the velocity, or I could measure the kinetic energy. I could measure all kinds of things here, right? But let's just start with position. If I measure position, what I'm going to notice is during simple harmonic motion, I'm going to get if I make a time graph, it's going to look like a sine curve or a cosine curve. It's going to be this sinusoidal graph like this. Now, my drawing program doesn't do it quite right, but let's just say it looks like this. Here's what's important with it, though. I can take this graph and I can very easily extract from it the period of my spring oscillator, because here it is at maximum displacement in the positive direction. Now it's going to accelerate. It's going to pass through equilibrium. It's going to go to the other side of equilibrium, slow down. And now here it is at its maximum displacement on the opposite side. And I'm at half an oscillation at this point. Now it's going to come back through the equilibrium point. And now it's going to complete that oscillation by returning to its original position of release. So between here And here I've completed one oscillation, and that took 2 seconds from 0.5 to 2.5. Or I could say, what about from here to here? Well, that's one complete oscillation. It went from here to here. So again, that's from 1.5 to 3.5. 2 seconds is the period of oscillation of this object. So I could use that then. So if I know, say, for instance, the spring constant, and I look at a graph like this, I can find the mass of the system because they say, I'm going to look at the graph. And this is a classic thing they give you, right? They're going to tell you the spring constant, what's the mass? And you got to say, I'm supposed to look at the graph and figure out the period. The period is 2 seconds, so I can replace t with 2. 2 pi is always 2 pi. And now I know the spring constant, so I can solve for mass. Similar, they could say, all right, uh, um, what is the mechanical energy of this? Well, the mechanical energy I'm going to find by using the amplitude. So again, if I know the spring constant is 40, I can look at this and say, well, I don't need the period in order to figure out the mechanical energy of the system, but I do need to know the displacement. So amplitude is the maximum displacement from equilibrium. In this case, it's zero point 0.4. Don't make the mistake of using the whole thing, because to get from here to here, I would have to put in a certain amount of energy, and that's going to all get converted to kinetic when it comes back to equilibrium. So at this point here, I say, well, I can see that my maximum displacement is zero point 0.4, that the mechanical energy of the system at maximum displacement is all stored in the spring. So I can say, well, the US of the spring is going to equal 1/2 the spring constant, which I was told is 40. And I can just, from this graph, I can see that it's 0.4. So 0.4 squared. I got to move my face because I don't know what it is. Move my face. Okay. It'd be 3.2 joules, as if we care. Thanks for watching. Wasn't that long, was it? See you in class.